Anyway, regression is one of the most important areas of all statistics, and it's occupying the entire second half of the course. It's the bread and butter of statistics. It's what you're going to need to, it's your take-home message. It's what you're going to need when you go out and you actually practice statistics in a realistic setting. So, we have two sources for our information, actually three. One is my lecture, but the other two sources in terms of reading are this book by Michael Lewis Beck, okay, Applied Regression. And then our textbook, of course. Both books are really great. The book by Agresti and Finlay is spectacular with regard to regression, and Michael Lewis Beck's book, Applied Regression, is also very good. I used to teach at the University of Michigan and in Ann Arbor for about 12 years at the ICPSR summer program, where graduate students and faculty from all over the planet used to come and take courses in advanced statistics, and I used to teach nonlinear modeling, differential equation modeling. However, I looked around at what my other colleagues were doing and their students, and all those students had these big fat regression books with complicated matrix algebra and all types of stuff inside, you know, really heavy duty stuff that sort of is intimidating. But inside every one of those backpacks was Michael Lewis Beck's Applied Regression. Every single one of those students had this. It is the best written book in the English language on the understanding of regression that exists anywhere. Full stop, end of story. It is really easy to understand. It explains it just the way you want to have it explained. So, Agresti and Finlay is also a really great book. But this is why I had you assigned Applied Regression, an introduction by Michael Lewis Beck. This is the SAGE series. These books are very inexpensive. I've written 3 of them. I've published 3 of these SAGE series books. They're really to die for. They're really great. They capture one thing that you need to know in about 100 pages. They're small monographs. They're really valuable. And this one for Applied Regression by Michael Lewis Beck, he's up at the University of Iowa City. Spectacular. So I want you to read it. I want you to make sure you read every word in it. It doesn't cover as much as Agresti and Finlay or some other larger regression books. You'll get books that are just on regression when you get your second course in statistics. It doesn't cover as much of it, but it covers all of the core, all of the essentials in a way that you won't miss any part of it. You'll understand it. So this reading is really important. I don't want anybody proceeding further without thinking that this book is good. You're supposed to read it. It supplements what I give you. All right? In addition, Agresti and Finlay's book is spectacular. It's a very good book on that. The only difference I have with what I teach in this course and Agresti and Finlay's approach is when they talk about dummy variables. They don't do it the way I think it should be taught. And so for that one section when we talk about dummy variables, we simply close the book and I explain to you how dummy variables should be taught. They use a method that's very common, and in terms of the strategies for writing a textbook, they made the correct decision on how to teach dummy variables because they teach it the way instructors all over the place expect it to be taught. It's just a stupid way to expect it to be taught. It's tied to an ancient software program, an early version of SPSS, and that method was necessary back in those days. It's not necessary anymore, but the legacy of how to do the dummy variable stuff has stuck into the lexicon, into the way of doing things, and so people still teach it. So if I was writing a textbook on statistics like Agresti and Finlay, I might be faced with the situation of having to talk about dummy variables the way they did. But the reality is, nobody should be doing dummy variables the way they talk about it. So for that particular section, we're going to talk about it a different way, and I'm going to show you how dummy variables should be talked about conceptually and in practice with today's modern software that's not limited to the stuff that was basically going back to the 1970s. So sometimes you get people doing things, even in statistics, that's tied to limitations in the software that's dated a long time before you were born. And you say, why are they doing it that way? Well, if you go back in time and you sort of see why they started doing it that way, there were problems in the software they had to overcome, and they did it to do that. And then it became sort of the way to do things, even though the problems in the software disappeared. But other than that one thing, the Agresti and Finlay approach and the Michael Lewis Beck approach, spectacular. And I want you to read those books closely. So we're talking now about regression. We're talking now about how to make a line go through data. Let's explain this. I travel a lot in Africa. I love farms. I love farms in Africa. Those mud walls, thatch roof things that you call huts are actually people's houses. They call them houses there, they don't call them huts. And they're extremely comfortable. And it's a beautiful place to live and a beautiful place to travel. It's gorgeous in many respects. And when I go there, I've got some relatives who have farms, and we talk about farming and stuff like that. And eventually we end up talking about one of the staples in Africa, which is corn. Corn. How do you grow corn? So, in the spirit of internationalism, I'm going to be giving you an example that's not social scientific, but agricultural. We're talking about corn, but it'll make a clear parallel with all the stuff we're doing in the social sciences. If I have a situation where I have rainfall, I want to be able to predict, I want to be able to explain how much corn I'm going to get based on how much rainfall. Rainfall is one of the crucial considerations in farming, especially in third world countries. If you have good rains, you have a bountiful crop and you have lots of corn, and not only do you eat the corn, but the animals eat the corn and everyone does well. Without the rain, the corn doesn't grow. So let us say we have, you can say it in terms of how many farms we have, and various farms all over the place, or maybe you have a big farm with a bunch of acres sort of scattered all over the place. So let's think of it this way. Let us say we have a big farm with acres that's somewhere on the hillside and somewhere on here on the flat land, but a big farm. And we're going to put a dot on this plot here where we have rainfall and corn. Rainfall on the horizontal axis and corn on the vertical axis. Now, the idea is that some of the acres on the hillside and over in that area and next to the hill, the winds come from that direction and the clouds hit the hill. So some of the acres that are on that side of the hill get a lot of rain because the clouds bump into the hills, and then they drop their rain. But the acres on the other side of the hill, they don't get the rain because the clouds go around the hill. You get the idea? There can be different reasons for more rain in some places than others. So you have a bunch of acres and a bunch of corn. Now, for every dot that I've placed on this graph here, we're going to call that an acre. And lo and behold, you look at that and you say, whoa, look at this. The more rainfall we have, the more corn there is. And look at this nice thing, a dot for each one. Well, this dot we're going to call a data cloud. It's a cloud. It's a bunch of dots. And we're going to actually see that those bunch of dots is in something called hyperspace. And what these dots are a realistic example of a graphic portrayal of the relationship between rainfall and corn. Now, in this hyperspace, we want to say, well, what is actually the relationship? Well, in the old days, pre-1970s, what they used to do, literally, is take a ruler. And they used to look a ruler here and just sort of, looks like it's about this. And they used to draw a line in. Let's put a few more dots up here. And say, that's the relationship. And then they literally used to measure, with a little ruler, what the change in y is for a given change in x. Delta y, delta x. And so we knew if x goes up so much, y will go up so much. There's a relationship there. So that's what we're interested in doing when we're looking at regression. We're interested in getting this line. The only difference now between now and pre-1970s is now we have computer programs that will give us the exact line, and we don't have to worry about the rulers anymore. So we will actually get the slope of this line, which is the change in y over the change in x, and we will also get the intercept. Okay? This is the intercept where the line crosses. I'm going to give you, how many people here have seen Jurassic Park? Remember Jeff Goldblum, the chaoticist in Jurassic Park? He used a lot of language, phase space, hypersurfaces and stuff like that, talking about, he was a chaoticist that was talking about the evolution of species and so on. Well, one of the things we're going to be saying is that in this thing what we have here, this line is actually a hypersurface. So when you go back home for break, parents can say, what did we learn in school? You can say, I learned about hypersurfaces and stuff like that. That'll probably end the conversation, but nonetheless, it's a good word to drop during coffee table conversations. You see, hypersurface is any n-1 space, n-1 surface. So what we have is, this is in 2 dimensions. Maybe we have 2 dimensions, corn and rainfall, 2 dimensions, okay? 2 dimensions, 2 dimensions. A line is 1-dimensional. So the line is a hypersurface. Okay? So we have a hypersurface going through hyperspace, and so what we have here is this 2-dimensional space with a hypersurface in it. Okay? If you ever take my 490 class, which is on nonlinear modeling, actually it's called modeling complex systems, we get into a lot of this stuff where we talk about phase space and hypersurfaces within phase space, and all of the models don't look at all like straight lines. I mean, they are wild. They go all over the place, and it's very interesting. But the bread and butter of modeling is regression, where you talk about straight lines. And so what we have here is a desire to draw a line through that. Now, if we have a variable here on our x-axis and a variable here on our y-axis, we're going to start using words to associate what those variables are. Now, depending on your discipline, or sometimes just depending on the people you happen to be talking with, the words change. So our x variable, the horizontal variable, is supposed to be causing or affecting our y variable. So this guy down here is a causal variable that's causing this guy up here to change. Corn is dancing because rainfall is pushing it around the dance floor. Okay? Now we use different vocabulary for this. The most common vocabulary is to call this rainfall thing the independent variable. And this thing here, the dependent variable. Independent and dependent. Now basically what that means is that on the independent side of things, you have this thing that's just sort of standing here doing its own thing. It doesn't really depend on anything else. It's just there. It's cool, it's hanging out, it's rainfall. Okay? But the corn wouldn't grow without it. So the corn is dependent on the rainfall, but the rainfall doesn't give a hoot. Does it make sense? So the rainfall is sort of independent of things, but the corn is dependent on the rainfall. So the rainfall, the corn is the dependent variable, and the rainfall is the independent variable. Now there's another way to think of it. Some people use the word endogenous instead of the word dependent variable. Endogenous. You'll see that word. You'll hear people talk about it. It means the same thing. Chill out. Don't worry about it. So, when they use endogenous, they're going to be using the word oops. I want to spell it right. Exogenous for the y variable, or the independent variable. So, endogenous for the dependent variable and exogenous, and they'll simply use them as synonyms, meaning they won't use the word independent variable and dependent variable, use the the endogenous variable, the exogenous variable, and so on. Well, if that's not bad enough, they have other words that go along with it. Especially if you take any courses in the medical realm, or biostatistics, or if you take anything in public health and so on, they use different words. So in this case, when they're dealing with medical stuff, they're dealing with drugs. Now, what kind of word do they like to use for drugs? Well, this patient is sick. What can I do here? Let's give this person this drug and see what happens. That's a stimulus. Okay? And let's see what happens. Do they live or do they die? There's a response. Do you get the idea? So we have a stimulus and a response. And so that explains, let me see if I have the exact page up here. The notation for the response and explanatory variables. That explains the usage that you sometimes see with Agresti, which is he's calling the dependent variable the response variable. That comes out of the medical field. Now he's still talking about the explanatory variable. And the response variable. So that's yet another situation. Okay, so they can use that. And sometimes they use words like stimulus. So the point is that the words sometimes change, but the concepts are always the same. In the social sciences, we typically use the word dependent variable and independent variable. Independent variable for the horizontal axis and dependent variable for the vertical axis. That's the most common. It's used almost all of the time. When you see changes in the social sciences from that vocabulary, it normally goes to the endogenous and exogenous. Okay, and that's usually people who are dealing almost entirely with methodology, statistics for what they teach and what they do, and sometimes they slip into the word endogenous and exogenous almost exclusively. So, but just make the translation when you're doing it. We're going to be calling it independent variables and dependent variables most of the time. All right? Now we are going to have an equation, and that's the whole goal of regression, to come up with an equation. We want to know what that equation is. And so, we want to know, we're going to have a y equals, and in the old high school algebra notation, mx plus b, where m is the slope and b is the intercept. So we're looking for an equation. Notice that this is a deterministic equation. Notice that x is given a value, multiply times the slope, add an intercept, and you get an exact value for y. That's not exactly what we're dealing with statistics. We have a regression equation here that in fact is an equation just like that, but our actual variables don't line up exactly. For any one particular value of x, you're going to get a range of values for y. So our values for y are not going to be perfectly predicted. Our values for y are going to be somewhat off. Now, the equation that we're actually going to use is not going to be using mx plus b. What we're going to be using is a more standard equation that uses some Greek letters, and those are beta. And so what we're going to be doing is we're going to be using y equals beta naught plus beta 1 x1. Now, why am I putting noughts and ones? Because right after we finish bivariable regression, we're going to be going into multiple variable regression. So here we have x1, which is, in this case, rainfall, causing corn output. So x1 is being called rainfall. Well, okay, well, what's the big deal? Well, we could have an x2. And we're going to cover that just in a little while. And x2 could be fertilizer. Yet another reason for corn to grow. So it could be that it's not just rainfall that's going in here, but also fertilizer that's causing increase in corn yields. But for right now, we're going to be dealing just with rainfall. But when we get to the fertilizer, we're going to be adding a x2 in there. And then you could also put in x3, which is the amount of work that the farmer is doing plowing the fields. And then you put in an x4 in there, which is whatever you're thinking of, okay? So this is the basic equation for a bivariate regression, and we're going to make it longer and add x1s and 2s, x3s, and so on. But basically, we're dealing with an intercept, and we're dealing with a slope. And we're dealing in terms of the mx plus b thing, of course. The intercept comes first, whereas in the high school days, we put the intercept last often, mx plus b. And the slopes is equivalent, the beta 1 is equivalent to the m, of course, and the beta naught is equivalent to the b. So we're going to be using this notation almost entirely. Now, the issue is that when you have a regression equation, there's going to be mistakes all the time. You're going to be predicting with a value for x, you're going to be predicting this spot on the y for the value of y here, okay? But there are going to be some people with some acres that have the exact amount of rainfall here that will get this amount of corn output or that amount of corn output. They'll miss the line. Very rarely will you have data actually hitting the line exactly. So this explains what we're talking about here, that the prediction equation has what they call a least squares property, when Agresti is talking about this. Now take a look at what he calls the sums of squared errors. We're going to actually change the notation a bit. And I'm going to be showing you different ways that we write that sums of squared errors. Sometimes we're going to be calling it a little different things. And I'm just going to be introducing different vocabulary that's basically used for the exact same thing. So no matter what book you crack open, if you look at something you say, okay, that's the way they're talking about that thing, you'll understand it. Just the same way as you talk about dependent variables versus endogenous variables versus response variables. If you see any of that language, you'll recognize what it is. So part of my job is not just to explain the statistics and to show you how to do it with the R programming language, but to explain the different vocabularies you'll get in different settings so you won't be fazed by it when you actually see it. So let's look at this sums of squared errors thing that's happening here. So what we see here is that with the sums of squared errors, SSE for short, because sums of squared errors takes a long time to write, let alone say. And then what you're doing is you're taking the y variable and you're subtracting it from y hat. What is this y hat? That y hat is a really cool thing. What we've been using so far in the course is y bar. And y bar is, of course, the mean. Y hat, with a little caret on top of it, is the predicted value. So if I want to say, for this value of x, what value of y am I predicting? This guy right here is my y hat. Okay, and it has this value right here. Okay, so that would be my y hat. Now, there is, of course, a mean. And for here, I'm going to guess it's around there. And I'm going to call that y bar. Now this is the key and one of the most important things I'll tell you with regard to regression. In the absence of any other information, if you only have corn to deal with, in the absence of any other information, meaning you don't know about rainfall, you have only one number you can predict, and that's the average. That's it. All of science is based on that. And that's not an exaggeration. All of science is based on that. Meaning, I have a y bar here, that's the average. I don't have any information for rainfall, so all of my dots over here get slammed up against the axis here and produce little marks along here. These are the values of y, corn, and this is the average, y bar. Does everyone see that? That means this axis doesn't exist, this whole plot doesn't exist, I have just this one line here, this is y bar, this is the axis for corn, and the values for the different acres go along here. They're scattered around. So this axis has, that variable has a mean, y bar. In the absence of any other information, y bar is the only thing that you can predict. As soon as you add more information, you get to predict better than y bar. So the whole game of regression is to see how much better you can get than y bar. Isn't that cool? Y bar is the basis. It's what you start with. And the regression is how much better can you get than y bar. Now in this case, as you add this axis for rainfall, you in fact are adding all of this new information. And based on this new information, these lines that are on the vertical axis get slanted out this way. And you can see how all the dots line up this way. So you can say, wow, now that I know rainfall, I can do way better than y bar. I can do y hat, which is a little caret on top. So the regression line is better than that. So the big comparison is, with regard to this, is the sums of squared errors. Are you going to be looking at that difference and comparing it to the difference when we had y minus y bar squared and adding that up? Remember when we were calculating the variance? And I always like to use this example just to rivet this in the mind so you realize how important this is, all regression. Because if you see it theoretically with statistics, it's sort of just a statistic. It's just something that's sort of boring. You hope you remember it. But I have found every time I mention this particular case, people say, oh, I get it. And they never forget it for their whole life. I asked you this one time before, but I don't think the video cameras were working at the time. So, when were you born? Approximately when were you, what year were you born? What was that? We have some ages here of 91, 1991, 1993, 1992. Okay. Until 1995, and this is something that scientists often try to revise. There was a recent article in Science, in the journal Science, where the author started it out so crazy I thought he was in a nut house. He basically started to say, we knew there were planets out there, we knew they were just around the corner, we were just waiting to find them. That's untrue. What actually happened was the following. Until 1995, astronomers all over the planet were arguing ferociously that there are no planets on any other star, not just in the galaxy, in the universe, that it was such an unlikely set of things to occur. So many things had to actually happen in order for a planet to form. It was very unlikely that it ever would happen. They were arguing that there were no planets anywhere, elsewhere, ever. Like not just the galaxy, the whole universe. Like we're alone. And then in 1995, the astronomers discovered the first exoplanet, the first planet around another star. Now, that happened in your lifetime. That means while you were, oh great, okay, you were small, all right? You were little, you were just toddler running around, but you were still alive. Astronomers, this is the ones that you take classes on, they were completely bonkers. What were they actually talking about? And what should they have talking about? Well, look, from a scientific perspective, there was only one thing they could have said. From science, strictly speaking, just as scientists. The only prediction they could have said was, we have a sample of one. What is the sample we had back in then? We had one solar system that we knew about. And that solar system had 9 major planets, an asteroid belt, comets, meteors galore, junk all over the place. They had no business saying that there were no other planets anywhere. The only prediction that could have been made was they have an average of 9, until we know more information, until we start discovering more planets, we have to predict the mean, which is on average there will be 9 planets on average, until we have more information. Meaning the only thing they could have used was a sample of 1, and that's y bar. And they had one solar system to look at, which was our solar system. And now, in your adult life, you're adults, they're discovering new planets like a few a week. So it's like, everybody knows there's planets out there. But in the old days, they weren't doing that. So you have to say, what were they actually thinking? They weren't thinking science back in those days. They were thinking their own emotions. If there were planets out there, then there's going to possibility be life out there, and all types of house of cards of thinking, all types of other concerns, theological concerns, personal beliefs, all that was influencing how the scientists were thinking. But from a scientific perspective, there was only one answer that could have ever been given. An average of 9. Period. Full stop, end of story. That's how many planets on average. Until you know more. So all of regression is about finding out that second part of the equation. Until you know more, finding out more. But in the absence of that, you've got the mean. So that's the basis of all of statistics. You start with the mean, what's the variation around that, and then collect more information to see if you can make a better prediction around what causes Y to be the way it is. Does everyone get it? I only use that astronomer example not because I'm picking on the astronomers. I could do the same thing with any field. I just like that example because it's so glaring, and I will probably stop using that example in about 5 years when my students are no longer under the age of 1995. Meaning when my students are being born around 1996 and 1997, then I'll stop using that example. But I like to use an example that occurred in your lifetime so that you can realize, wow, if mainstream scientists could have made that big a mistake, I bet there's tons of things that I can discover. So that's the type of energy you should be putting into the field of statistics, into the field of science, saying, hey, I bet there's a whole bunch of stuff, because that happened in my lifetime. That wasn't something that happened back in Galileo's day or Copernicus's day. I was alive when that happened. So that should tell you, how much there is still yet to be discovered. So what we are trying to find out right here is this Y hat. And we're making a competition between Y hat and Y bar. Now let me give you an example where we don't get the information we need. Look at that data cloud. We have two axes, X, Y, and that data cloud. That looks like a globular cluster. It doesn't seem to be going up, and it doesn't seem to be going down. It's just like hanging out there. Let's put a regression line through that. It's flat. What does that mean? That means as far as this variable is concerned, we didn't add any information to it. And in fact, we're still no better off with that variable, that new variable X, than we were when we just had the mean. So having this new variable just didn't help us. So what we're looking for is variables that do help us, that do explain certain things. And that's what we're trying to get. We're trying to find variables that actually, when they get higher in their values, the relationship between Y and X becomes clear. And in the first example, I had a situation where the relationship went up as X got bigger, Y got bigger. But we have also inverse relationships where as X gets bigger, Y gets smaller. But it's so easy to see. So when we have a relationship that goes down or up as X changes, we have information over and above the mean that matters. So we have three types of variables. We have variables as explanatory variables, that as the explanatory variable goes higher, our dependent variable or endogenous variable, that also goes higher. We also have where the explanatory variable gets higher, the dependent variable gets lower. And we also have when the explanatory variable gets higher, the dependent variable doesn't even notice. It doesn't even matter. And so you just get a globular cluster. So we have a relationship that goes up, a positive one, relationship that goes down, a negative one, or no relationship whatsoever. And we have gradations in between, of course, but that's the basic threefold categorization of it. Things go up, things go down, or they don't go at all. So the variables that produce relationships that don't go anywhere, they're no different than, I didn't get any information from them. I could have just stayed with the mean and I'd be very happy. Okay? In that situation, let's redraw that. Look what it means to the line. If the mean was as good as I could get, well, what does this mean for this line? That means as x gets larger, you're not going to be predicting anything more for y, or less for y. That means what? That means this thing here. What will be the slope? If x gets bigger, or x gets smaller, we don't want it to affect y because nothing happens to it. So what does the slope have to be? If the slope is a number like 1, if x gets larger, you're going to be adding stuff to the y value, okay? So your predicted value, okay, your predicted value for y is going to go, say, up if x is positive 1. But if we don't want that to happen because the relationship doesn't change, what must the slope be? What number must it be? If we don't want this to affect it, if we don't want x to affect it, what must beta 1 be? It can only be one thing. What's that? Not 1. If we made it 1, then any value we had for x would be added to our predicted value, and we'd go up or down. We don't want that to happen. 0. So the big thing with statistics, with regression, is this slope. This slope, is it a real number like a positive or a negative thing? If it's a negative thing, we're predicting y to go down when x gets larger. If it's a positive thing, we're predicting y to go up if x gets larger. But if it's 0, 0 times anything goes away. If it's 0, then 0 times x, nothing happens. And then what is beta naught going to be? You're predicting y hat based on only the intercept. And what will the intercept be? What is the intercept? If the line is flat, that means the slope of this line is 0. That means your beta 1 is 0. So what is the intercept? The intercept is the same thing as the mean of y. So the intercept is the mean. As beta 1 becomes more important, then it will have a relationship, and then the intercept will no longer be the mean. And the line will actually take a form and be useful to us. Okay? So that's what all of statistics from now on for the rest of the course is about. We're going to be saying, is that slope important to us? Now, we already started doing some stuff early on when we were saying, is one mean different from another mean? Remember we were using a t-test for the difference between the two means? Now, what is going to be the essence of everything that we're thinking about from now on? We're not thinking about, is one mean different from another mean? We're going to be looking at a slope, beta 1. And what we want to know, is that slope a real thing? Meaning, do we have a relationship between x and y? Is this slope a real thing, or is it 0? So what we're going to be doing for the rest of the course is saying, what we're interested in is that slope, and the test that we want to use is that slope different from 0. That's it. If it's different from 0, remember you can never say with statistics that a number is different from another number unless you test it. You can't say a 2 is different from a 3. You have to test it. So what we're going to be doing is saying the following, and this is really important. Listen up. This beta 1 is going to be a statistic. Remember how we had a formula for the mean? And then we had a formula for the standard deviation? And remember I said in order for the formula for the standard deviation to be unbiased, which is going to be demonstrated to you in your next course in statistics, you had to divide by n minus 1 rather than n. That means that formula for the standard deviation was like an arrow. You're shooting and you want the arrow to be straight so that it shoots straight at the target, which is the standard deviation. Well, that formula is your instrument to estimate the standard deviation. This slope is going to have a formula, and that will be the instrument to measure what the slope is of this line. So, what we are going to be saying is, for this statistic, will that statistic test differently from 0? Now, with every statistic you get, just like when we had a mean, what did we say? Means and other statistics, they don't have standard deviations. What do they have? Populations have standard deviations, but we had to come up with a different word. Statistics, that's right, statistics had standard errors or standard mistakes. Okay, so if we had 18 people going out to do little surveys and coming back, and we compared them, we'd all get different averages. Each average wouldn't be exactly the right average, so we'd have a standard sort of error. That means each one of these statistics that we get, the slope, will be like a mean in the sense that it's a statistic. And it's aimed at the population guy. It's aimed at the real guy. And we're wanting to shoot straight. But if we do the regression a whole bunch of different times, there'll be, with different samples, we'll get different numbers. There'll be different numbers because each sample will produce a little different number. And it was just like our samples for the means, there'll be errors associated with it. There'll be a standard error. So this beta 1 is going to be a slope with a standard error. And we're going to be doing a very simple thing. We're going to be saying, I want to know if that slope is different from 0. How do we do that? Well, we go beta 1 minus 0, because that's the distance between beta 1 and 0. And I want to measure that in standard units. So how do I make standard units? Divide it by the standard error. So it's the same way we did with the means. I'm going to take the difference between these two things and divide it by the standard error. And to give you an idea, well, actually, let me just put the standard error here. We actually use a nice notation a very simple notation to tell you it's the standard error for the particular thing we're looking at. But in this case, it's quite clear because we're dealing with just the beta 1 here. So we're going to be looking at the distance between beta 1 and 0 in standard error units, or standard deviation type units. All right, standard error units. And what do we know? If this division is bigger than, say, 1.96, we're 95% sure the difference is different from 0, that this slope is different from 0. Does it make sense? So that's sort of the nutshell encapsulation of where we're going for the rest of the course. We've got a dependent variable, an independent variable, a data cloud. We're shooting a line through it. We're going to be calculating what the intercept is and what the slope is. And then we're going to be testing whether those slopes are different from 0, meaning are they a real thing? And if they don't test different from 0, then we cannot reject the null hypothesis, which is that there's no relationship between the variables. The alternate hypothesis is that there is a relationship between the variables. Okay. Let me cover just very briefly the idea of the mean squared error, because it follows nicely with the discussion we've had so far. And this is from page 267 of your book. You see, there is a distribution, a conditional distribution around the regression line. Why do they call it a conditional distribution? That means for different values for x, meaning given a value for x, what is the distribution around the line for y. So you're not just looking at the deviation for y around its mean, you're looking at the deviation for y around y hat, which is the progression, which is the line. We're going to call that the regression line. So what we have here is, if we take the value for y minus its predicted value. So here's the predicted value for one guy right here. For this value of x, okay, let's call this just a little value for x here. That gives us a value for y here. Okay, now let's look at that guy right there. See that dot right there? Well, it made an error. It didn't quite predict. This is the line prediction, y hat, but the actual guy was up here. So the actual guy is y, right here, minus the predicted, which is y hat, which is the point on the line. Now, if I'm going to say, well, what's the average of those guys? There's a problem here, you see. If I go this minus the y minus y hat, I'll get a positive subtraction. But if these guys down here minus y hat, these are below the predictor, that'll give me a negative number. And if I add them all up, I'll just get 0, so that's not going to help me. So I got to get rid of the negatives. So how do I do that? Nice. We do it the same way we did before, which is the squared, the squared term. So you square, so what you're taking here is you're taking the y minus y hat and squaring it. Now notice here you're dividing by n minus 2. That goes back to the same understanding that you had when you were calculating the variance, when you had to divide by n minus 1. Now I'm going to give you, in your next course in statistics, you'll have an algebraic reason for why you have to divide by n minus 2. But I'm going to give you the intuitive reason. Okay, it'll make sense. Remember when you were dividing by n minus 1 for the variance or standard deviation? I said the intuitive understanding is how much more information did you, in order to calculate the variance or standard deviation, you needed more information than the mean, because the mean is inside the formula. You can't calculate a standard deviation with only one observation. You've got to have over and above that. So what your degrees of freedom are with respect to that one observation are n minus 1. Because you have, let's say, 10 observations, you needed the 1 for the calculation of the mean. So how much extra information you have is the standard deviation is based on that 9 pieces of extra information. That's the intuitive understanding of it. N minus 1 for that formula when we had, remember we had the idea of x minus x bar squared summed up divided by n minus 1 for the variance, okay? And it was always y divided by n minus 1 rather than n, because you're getting the average of the squared deviations, okay? Because of that extra information, because you had to have some information. One observation had to be used at least to give you the information for x bar. Now the intuitive information is, why is this n minus 2? Why did the degrees of freedom change? How many numbers did you have to calculate, did you have to have in order to have a y bar? I mean a y hat. For a y bar you needed only 1, right? But for a y hat you need how many? 2. You have an intercept and a slope. Does everyone understand? So this guy here had 2 other numbers, 2 other statistics buried inside of it, this y hat. So how much other information did you need in order to be able to calculate what the deviations are around that? You needed n minus 2 extra pieces of information. Again, that's not a very satisfactory answer from an algebraic perspective, but it's a lot of fun when you get to your next course in statistics to actually go through the algebraic deviation for why that actually happens. And but I want you to have the intuition settled in your mind so that when you actually go through the actual calculations and you actually see, to make this unbiased, you actually have to divide by n minus 1, or n minus 1 in this case, or n minus 2 over there. So you actually see the algebra work out. I want you sort of to be, what I don't like you to do is to go in without any feeling of intuitions or any feelings of why it should be. It just feels like magic. And then sort of to take it on faith and to wait for the formula to be shown to you, the derivation. That's very unsatisfactory. So on an intuitive level, I like you to be able to say, I get it, I understand why intuitively they're dividing by something like that. So what they're getting here with the sums of squared errors, they're taking the sums of squared errors around y hat, squaring it, of course, adding them up, dividing by n minus 2, and taking the square root of that. All right, which measures the sample variability around the least squares line. So it measures the variability around the least squares line. Now, we are assuming that for this regression stuff to work out the way we're doing it, sort of basic mode, we're assuming that that's going to be constant. That means that we're assuming that, and there are situations where it's not constant, and we have to do some things a little different when it's not constant. But we're assuming it's not going to look like this. Does everyone see here? As the regression line goes up, this is just one example of many. Look how the errors around the regression line, they fan out. So for this particular thing, we're assuming that the mean squared error is constant across the entire range of x values, meaning it's sort of a uniform distribution around the regression line. Are we okay with that? For this thing to work. When that doesn't happen, what you have, this is called a this is weird vocabulary. I don't know where they came up with all of this, but this is called homoscedastic error, meaning your error term is uniformly distributed around it. But when you have it not distributed around it in an equal manner, so you get a constant mean squared error, but you have it sort of distributed like this, where you have that funnel shape, or another crazy shape, any other shape that's not sort of, any shape that's not sort of like where the data cloud are in there, and you get an equal distribution around this regression line. That's homoscedastic error. Anything that's different from that is called heteroscedastic error. The vocabulary is wild and crazy when you get into the statistic, but it's really great. You memorize the terms, drop them on coffee table conversations. I mean, you stop the coffee table conversations right there. They just look at you and say, you're one of those smart dudes, aren't you? And I mean dudes in the dudes and dudesses manner, men and women. So the point is, this is a situation where this would sort of violate this idea of a constant mean squared error. But that's what the mean squared error actually is. There are ways to get around this. And there's actually controversies for the ways to get around it. There are statistical ways to get around it. You change the formulas to sort of smoothen things out and flatten it out. And then there are other people who say, no, you don't change the formula. That's like killing the butler and then burying the body, so you're getting rid of the evidence. You're doing statistical methods to sort of fix something that's a problem. There are other people that say, don't do that. You're throwing the baby out with the bathwater. What you're trying to do is you've got to have a different model so that your error doesn't do that. So you have to change the irrational model. And you get methodologists that are sort of yelling at each other for the right way to go about it. So if you thought statistics was dull and boring, it's absolutely not. There's a lot of yelling and shouting that goes on. And they get very emotional and the blood pressure goes up, yelling at people, what's the best way to go about all these problems? Well, anyway, that's one of those problems that actually occurs. So that's one of the mean squared error thing gets involved in it. Now, actually, I'm going to introduce something that's a little different from the book. But it really makes a lot of sense, and it's just a very slight deviation from the book. And you'll see why. You'll read the book and my understanding has been that when I've explained it this way, it sort of sticks into the students a little better. And this regards the discussion of what we call the R-square, or how well the regression line fits the data. Meaning, if you have X here and Y here, and a regression line there, and data sort of around that, versus this, okay? If you were to look at these three plots, you'd say, this regression line fits these data really well. Do you see how nicely these data are clumped around the regression line? I mean, it really looks like it's a very tight fit. I mean, it really looks like as X goes up, you really know how you're going to predict Y. Because look, those little dots really hang close to that regression line. This one, not so bad. I mean, not so good, but it's not terrible either. As the X goes up, the line goes up, and you can still see the trend, but the data points aren't quite so closely gathered around the line. So the line's not doing as good a job, but it's still good enough for government work. Now this one, on the other hand, this would bring down the government. Look at that. X goes up. Wow, look at all that error around the regression line. That regression line is not telling us very much. There's dots all over the place. They seem to be going way high and way low, and looks like a bad thing. Well, we'd like to have a number that would sort of summarize how well these dots hang close to the regression line. Okay? Now I'm going to actually write the formula. The formula actually is the exact same as the one in the book if you rearrange the algebra a little, but I write it this way because it's written this way in some other books, and I happen to like this way because it makes really intuitive sense, and I can explain it once to you and you will say, okay, that's cool, I get it, there's no problems. So we're going to call something R squared. Now notice I'm using a small letter for the R. R squared, that's small letter, very important, means a bivariate regression. That means only two variables are involved. Bivariate regression. If two variables are involved, we use a small R square. Right after we finish with bivariate regression, we're going to be going to multiple variables. So that's multivariate regression. And then we will use a capital R square. So in your final exam and in any of the other stuff that you deal with, if you're dealing with two variables only, you're using a small R squared. If you're using more than two variables, it's a capital R squared. But for right now, we're going to be using the small R squared, okay? Conceptually, it's the same thing. It's just two variables or more than two variables. Now this looks a little different than the stuff that you get in the book for the R square. But it's actually the exact same formula. But this one is really easy to explain. 1 minus the residual sums of squares divided by the total sums of squares. Residual sums of squares? Wait a second, what's that? I thought we were dealing with the sums of squared errors. We were! It's the same thing. So some people like to call it the residual sums of squares, and some people like to call it the sums of squared errors. So let me give you an example of where they call it. Here we go. Okay, and I'll even go so far as to put my little notes here. Okay, on the board. So I use the RSS instead of the SSE, and that's also confusing because some people, the RSS actually stands for the regression sums of squares, which is a little different. So you actually, and I think regression sums of squares is what Mike Lewis Beck uses. So the notation varies depending on what book you're using. Again, it's not a mistake for me to introduce different ways that these things are talked about, because I don't know what teacher you're going to get and I don't in the future, and I don't know what book you're going to be using in the future. So I've got to introduce to you the different language that's used in all the different places so you recognize it. Okay? So Agresti and Finlay use it a little different language than the stuff they use in the Michael Lewis Beck book. So let's go through this. This r squared is this thing. Now notice, before I explain my formula, which is 1 minus RSS over TSS, let's just be settled that it's the same exact thing. I'll explain it from my side of it, but let's show you that it's the same thing as what Agresti and Finlay does. They have total sums of squared minus the sums of squared errors divided by the total sums of squares. Let's divide this out. Total sums of squares divided into total sums of squares is going to equal what? 1, right? That's where that 1 comes from. And then total sums of squares divided into sums of squared errors, well, that's exactly the same as here, but I'm using the RSS instead of the SSE. But it's exactly the same. Okay? And some books will have this called will call this RSS. I think the majority of books use SSE, and the minority uses RSS. So why do I use the RSS? Because it stands for residual sums of squares, and the word residual is very important in statistics. The word residual makes sense intuitively, and it is the difference between any value you have here for y and its predicted value. That is the residual, and that's how you're taught in all of statistics, that the difference between the actual y value and its y hat, the predicted value, is called the residual. So, why call it the sum of squared errors if the thing is called the residual? You get the idea? Now, it's okay. It's not a big deal. You can do that. In your next course, they may do that. But some statisticians like to call it the residual sums of squares because it makes sense that this is a residual, so just call it the residual sums of squares rather than the sums of squared errors. I mean, if I wanted to call this the error, which some people do, then the sums of squared errors is perfectly okay. If I want to call it the residual, let's call it the residual sums of squares. Is everyone okay? The only confusion that sometimes happens is that some statisticians and some books called RSS stands for something else called the residual sums of squares. So, which is the converse of it stands for the regression sums of squares, which is the converse of the residual sums of squares. If that's how much is not explained, then 1 minus that is the amount that is explained, that type of thing. But let's not worry about that. The issue is that in this particular way of looking at it, RSS is the same as the SSE, and it simply is the residual sums of squares. Okay, and that's exactly what we have here. So look at this. This is so easy to explain and have it feel good intuitively. The r squared is 1 minus the ratio from the residual sums of squared divided by the total sums of squares. The total sums of squares is like the variance. Okay? The total sums of squares is like the variance. It's the value of the y minus its mean. Okay? This residual sums of squares is y hat. It's your y minus your y hat squared, adding those up. So what you're doing is you're summing up this. You have the y minus its y hat squared added up divided by the y minus the y bar. Okay, so it's the ratio between the two. Now let's look. What if the regression sums of squares, what if the regression itself isn't doing squat? It's just not useful. It's doing no better than the mean. Then y minus the mean, you're going to get a big data cloud here, and the mean will be just as good as the regression line. Okay, it'll be something like this, big data cloud here, and the mean and the regression line will be about the same. So if y minus y hat is no different than y minus y bar, what is this division going to be equal to? Meaning the variation around y hat is going to be the same as the variation around y bar. So what's this division going to be equal to? If this is the same as that and you're dividing it, what do you get? 1, right? What's 1 minus 1? 0. So the worst that the r square can get is 0. And that means there's no relationship between those variables. What, on the other hand, if you have something that's like this, or even better, that the regression line and the predicts perfectly and all the dots line up on the regression line exactly? What if you have something like that? What's the difference between y and the y hat? If all of the data points line up exactly on the regression line, what's the difference between them? 0. There's no difference. Your predicted is exactly what you actually have for your data. So this will be 0. And 0 divided by anything is still 0. And what does this thing go to? It goes to 0. And what's 1 minus 0? 1. So r squared tells you how well your regression line is doing. And if it's close to 0, you didn't do so well. And if it's really high near 1, hey, mazel tov, you're great, you're doing wonderful. Does it make sense? You're explaining a lot with your regression line. R squared is a really great thing. You've got reading to do for this weekend. Tests come back on Tuesday. See you then.